face, and I flip, and then you can see the back of my hand, the other face, like heads and tails of a coin. Right? So let's list now the symmetry operations total of D4. Now D for dihedral, remember? 4, that's the number of sides, so we're talking about a square now, or the number of vertices, it's equivalent. Okay. Now this operation that does that, let's call that H. H for the flip about the horizontal. Right? And similarly V, that would be the symmetry operation that does that. That's the flip about the axis V, little v. L is the flip that does that symmetry operation. Okay. And M is the one that does that. Right? Now they're the hedral type operations. Now you've got for rotation. Do I have a square? Yeah, I have a little square here. Okay. So operation I is do nothing. So I just did I. Okay. Now let's see. So my clockwise is your anti-clockwise. So that's R. And 1, 2, that's R squared. And 1, 2, 3, that's R cubed. Okay? So R is the rotation anti-clockwise by 90 degrees. This is anti-clockwise rotation by 180 degrees, like double. And this is the symmetry operation, rotation anti-clockwise by 270 degrees. In other words, 3 times this one. Okay? And the do nothing. Right? So, so we can map, this way. We can map these 8 symmetry operations. That's the total, 8 of them for the square. And so that's your group. These are your symmetry operations on a four-gon. A four-sided regular polygon. So the 4 sides have equal length. Okay. Now the binary operation is just simply followed by, meaning do this operation first, followed by another one, one of these. Okay. Now you're mapping these symmetry operations into permutations, okay, in this way. And what are you permuting? You're permuting the vertex numbers. Right? So, for example, in the case of the square, let that be vertex 1, 2, 3, 4. Now, as you perform these various symmetry operations, these vertices are going to move around, right? They'll change. So, so the set of 1, 2, 3, 4, those vertex numbers, they get permuted into something else, right? And that's what this is doing. So if you're mapping these symmetry operations, that's this set, or actually group, into members of the symmetric group of 4 objects. And what are your 4 objects? Well, the vertex numbers. Okay. So so what is the symmetry operation H? This operation. What does that map into in terms of a permutation? Right? It's the product of 2 transpositions. Okay. So 1 goes to 4 and 4 goes to 1. Does that make sense? This goes to 4 and 4 goes to 1. Well, that makes sense, right? Because you're flipping it. 4. If this is 4 down here and you flip it, it'll be up here. So 4 goes to 1, 1 goes to 4. And similarly, 2 goes to 3 and 3 goes to 2. Make sense? Right? Now, if you've got that idea, so this permutation here is just the product of 2 transpositions. Remember, a cycle of length 2 is called a transposition, and we have 2 of them. So you could say that this permutation is even, right? Remember that? Okay, similar logic here. Now it's the V, so you're doing this. So the 1's going to swap with 2. So 1 swaps with 2. Transpositions are just swappers, remember? And 3 swaps with 4. So 1 swaps with 2, 3 swaps with 4. Now L, what's that doing? L, that's this way. Now 2 and 4 won't change, right? It's only 1 and 3 that flip. So you just got that. 1 goes to 3, 3 goes to 1. And M, similar story. So the 1 and 3 will not change, but the 2 and 4 will flip. So there's your transposition. That 2 goes to 4 and 4 goes to 2. Right? So these things on the right hand side, they are permutations. Right? And the things in the brackets here, they are symmetry operations. Right? And when mapping, here it is here, we're mapping from the set, actually the group, of symmetry operations, this group, D4, the dihedral group of 4 regular sides. Well, it has to be regular to be a dihedral group. Okay, so so you got here now eight permutations. These are permutations. Right? Now the size, the order of the symmetric group of 4 objects is 4 factorial. That's 24. So the order of S4 is larger than this group. This group here has 8 members. Its order. The order of this is 8. Right? Here they are. Here are your 8 members. Symmetry operations. And this is a group, and that's a group. But the order of this one's larger than this one. It's 3 times larger. Okay. So this group is in actually a subgroup of this one, and this subgroup, these 8 are in fact a subgroup of this. Right? You could show that if you want to do that for homework. Right? These 8 are in fact a subgroup of the symmetric group for objects. And you can also show, again, do some homework if you like, that the dihedral group of 4 sides, D4, is isomorphic. Is the isomorphic sign here? Is isomorphic to this subgroup? These 8 permutations. All right. Well, we've got these 8 symmetry operations. It's a group, and we could create the group table. Now, the order of this group is 8 members. So the size of the table is 8 by 8 squared, which is 64. So obviously I wrote this out before, and it took quite a while, as you can see, a lot of work, very boring. But it's all there, and the fact that I'm using like 8 members is now kind of lead-in, and I ran out of board, so I'll have to go to a new session. But what I'll do next is I will scrap this approach. I will then go looking for a fewer number, not 8, a fewer number of elements of this group that generate all of these. Remember what it, like in the context of a what's the word? Cyclic group, you have a generator. So that's one element, and you take that element and create powers of it, like little g as you generate, g to the n can, n as an integer, you just, as n increases, you generate, you create, you make all the elements of your cyclic group. Now, we've also talked about something called a minimal generating set. So in the next session, I will take two of these, and I'll show you that I can generate the whole thing, and it will simplify this down quite a lot. So and something will come out of that called the presentation of a group. So that will be next. And before I finish off, have a look at this group table for D4. You know, it's getting large enough to start showing a bit of structure. I mean, look. Here you got sort of like 4 blocks within the whole table, and like this block here, the results are rotations. They're all rotations here in this block, and similarly here. So this would be the northwest block, and this is the southeast block. Okay, and they're both the results. You know, the result of the binary operation of one here and one here. They're all rotations, and this block here, the southwest block, and here's the northeast block. These are all reflection type, flip type operations that result. So what you're seeing here is the beginnings of structure within a group. And as the groups get more and more complicated, they have increasingly greater structure. And you may be able, like if you had a much larger group, you may have structure within structure. And then there's a whole, especially at M1, Masters 1 level, there's a whole analysis of going down from the big group into smaller groups and smaller groups, and so on. And so this is like a foretaste of what's coming at the next year up, when if you're interested, come and do first year masters M1 level finite group theory, and we can do this kind of stuff. Right, I've run out of board, so I'll stop here, and in the next session I will show you how to generate this group using just two generating members. In fact, one of them is this one, and the second one is one of, it doesn't matter which one, but one of those 4. Okay, and together, plus a few relations, and I'll explain what that is a bit later, we can build the whole D4. And then we can generalize that idea that comes out of that and go to Dn and generalize it, where n is the number of sides on your polygon. It's an n-gon. Okay, stop there.